Hey everyone, welcome. Good morning and welcome to the CAE Fall 2025 seminar series. Today's talk is a double event. Khashayar Heydarpour and Husam Farghal, who are PhD students in civil architecture engineering at will talk about experimental and field evaluation of SEAHIVE for coastal and bridge scour protection. Khashayar is a PhD student in civil engineering working under the supervision of Dr. Nani. His research primarily focuses on experimental and analytical evaluation of advanced concrete systems reinforced with GFRP, including SEAHIVE for coastal and bridge scar protection. Husam is also doing his PhD in civil engineering under the supervision of Dr. Nani. His research is centered on the experimental and numerical evaluation of cementitious materials reinforced with GFRP and steel, with a focus on enhancing their structural performance and durability. Thank you very much for doing this. Khashayar, all yours.
Hi everyone. Today we are presenting the experimental and field evaluation of SEAHIVE for coastal and bridge scour protection. I am presenting this with my colleague Husam. To begin with, we want to know why shoreline protection matters. Based on the reports, over 40% of the US population reside in coastal areas, and over 29,000 miles of coastlines exist in the country. And it has been reported that $2 trillion damage is due to the weather-related disasters, and it increases the urge for protecting coastal infrastructures. And the figures on the left shows two recent hurricanes in Florida, Hurricane Milton, which occurred a couple of months ago, and also Hurricane Irma. There are some conventional countermeasurements for protecting shorelines, and the credit of this work is basically for Dr. Husseinzadeh, Dr. Khashayar, and Dr. Barbarigus. One of these measurements, typical measurement, is actually concrete seawalls that come with unique configurations, including vertical, curved, and riprap. They individually have their own advantages and disadvantages. However, our goal is to explain the disadvantages of these conventional shoreline protection methods. One of the disadvantages is the poor ecological performance due to the low surface and lower structural complexity of these seawalls and these typical protection methods. They offer fewer attachment points for microhabitats, and the second disadvantage is the induction of scour and erosion due to the strong wave reflection, and also corrosion and durability issues such as steel corrosion, cracking, spalling, and structural degradation. And there is also high construction and maintenance cost for the seawalls. And they also have environmental and aesthetic impacts. As a result, SEAHIVE is introduced as a solution for coastal protection with these benefits. The first one is wave energy dissipation, and it happens when the water passes through the void units of the SEAHIVE, and it leads to more efficient wave energy dissipation. And the cavities in units are suitable for growing marine habitats. And they also have a higher durability due to the potential for using FRP reinforcement that are corrosion resistant. And they are also easier for installation, and the installation of the SEAHIVEs will be also explained at the almost end of the presentation. SEAHIVE is also known as a solution for bridge scour protection. Description of a scour is very complex, like how it happens, when it happens. It has a complex dynamic. However, The preliminary concepts propose that wrapping bridge piers with SEAHIVE will alter the water flow patterns around the pile cap, and thereby it helps minimizing the scour at the bridge piers. One of the first studies that was conducted on SEAHIVEs were the units internally reinforced with GFRP bars. The credit of this work is majorly for Mirdar Soltani during his PhD studies. In this study, 4 specimens were tested. 2 of them, CB1 and CB2, were under pure compression, and the 2 other SEAHIVE specimens were under 4-point bending. And here is also the configuration and reinforcement details of the SEAHIVE. So the longitudinal reinforcement includes 6 number 5 or 15M GFRP bars, along with number 3 or M10 transverse reinforcement. The first 2 specimens were tested under pure compression. The schematic view of the specimens can be observed in the figures, including the configuration and also the placement of strain gauges. And it was observed from this experiment that the first crack occurred at the location of the holes and then propagated horizontally, as you can see from the image. Image B, the crack propagated horizontally along the mid-depth of the leg. Also inclined cracks, possibly due to shear, started after initial horizontal cracks, and the failure occurred when the horizontal cracks grew in length, connecting holes in the hexagon. And the other 2 specimens were tested under 4-point bending. And you can also see the schematic view of the test setup. And it was also observed from these experiments that the horizontal cracks formed at the mid-leg between the holes, and failure was initiated by arcing with a combination of crushing of the concrete toe and the slippage of the longitudinal reinforcement that was not properly anchored. So in another study that was recently done, the pre-stressing is applied to improve the performance of the units and also to control the cracking. So right here we have 7 full-scale specimens with the length of 4 meters that were fabricated and tested in this study. Specimens A1 and A2, these 2 specimens, are moderately pre-stressed with the concrete compressive strength of 72 megapascals. And specimen D1 is also pre-stressed at the same level, but with lower concrete compressive strength. And the specimens B1 and B2, C1 and C2 are highly and slightly pre-stressed, respectively. Right here we have the configuration of these 7 SEAHIVEs that share the same configuration. The length of each specimen is 4 meters, and also they also have a height of almost 80 centimeters and the width of 90 centimeters with the thickness of 127 millimeters. The perforations and the openings on the faces of the SEAHIVE are both on the side legs, as presented in this figure D, and also bottom and top flange of the SEAHIVE, as presented in figure E. Now let's start with the fabrication of pre-stressed SEAHIVEs or PC-SEAHIVE specimens. In the beginning, the steel molds were fabricated, as presented in this image. And the completed mold consisting of the steel hexagonal shape and also the cones, the steel cones for creating the perforations, was also patented by Sigma C company at Italy. And the GFRP bars were then pre-tensioned using hydraulic jacks and were locked with these anchors as presented in this figure. The anchoring was done to make sure that the pretension remains in the specimen until the concrete hardens. And after 24 hours, rebars are cut and the demolding begins. And the specimens are ready to be tested. Before testing the specimens, the material characterization was carried out on the number 4 longitudinal GFRP bars. And also the concretes were tested using cube test that is more popular in Europe. But ASTM uses the cylinder test made mostly in the US, and the equivalent cylinder test results are also brought in the paper. So overall, it was designated for specimens A, B, and C to have the compressive strength of 72 megapascal, and specimen D to have the compressive strength of 43 megapascal. So right here we have the 4-point bending test setup in this figure, where we can see that the overhang length is 36 millimeters, and we also have the shear arm of 1,224 millimeters. And no strain gauges were attached to the specimen. Under 4-point bending test, like here we present the test results for each of the specimens, and mostly for all of them under 4-point bending test, the first flexural cracking occurred, and it started from the tensile fiber at the bottom flange up to the mid leg. And sudden brittle failure of the specimen at the end in the failed mode represents a premature shear failure that occurred at one end of the specimen, where the shear is maximum and the transfer of pre-stressing is minimum. And the same scenario was observed in all other specimens, although with different cracking and ultimate load capacities. At the end, we can summarize the tests like this, that the increasing the pre-stressing level effectively increased the cracking load and ultimate flexural capacity of specimens. And we can also say that premature shear failure occurred in all specimens, and pre-stressing was also more effective in the midspan due to the transfer length. For analytical evaluation, the perforated geometry of SEAHIVE units are represented through cross sections, and the results right here, like 4 different cross sections, including no holes at the cross section, no openings, and openings only on the top and bottom flange, openings on the web or side flanges, and opening on each of the legs or on the flange and on the web. And the results at the end are compared with the experiment to come up with some accurate section for analytical evaluation. The main design provision for GFRP reinforced concrete structures is ACI 44011. and also other ACI 440 specifications. However, pre-stressing is not included in this code. And as it was observed from the tests that pre-stressing significantly affected the cracking capacity of the structure, it was decided to use the formulation at ACI 31819 or recently published ACI 31825 for the analytical part. In this equation, we can see that Fr is the modulus of rupture of concrete, and it is obtained from this formulation. And lambda is equals 1 when we don't have a lightweight concrete. And the cracking moment can be obtained from also the modulus of rupture and also the concrete stress due to the precompression, FPE. And using the beam theory, we can get to the formula that the cracking load is 2 times cracking moment over the shear arm of the specimen. That was 1,224 millimeters. And here is also the serviceability analysis results using different cross sections and their comparison with the test result. And as it is evident from each of these figures, we can say that the specimen with openings in all legs and also the specimen with opening at the top and bottom legs have had the nearest cracking load capacity, analytical cracking load capacity compared to the tested specimen, and it corresponds to the loading direction of the test. This one is for specimen A1 and A2. These two, again, the same pattern was observed and the difference was very low for specimens B1 and B2 that had the highest pre-stressing level. The specimens C1 and C2, they had the lowest pre-stressing level, and we can see that the pattern remains the same almost, and like the analytical formulation was able to somehow get accurate response. And also specimen D that we got almost the same value for the analytical evaluation and also the test, where we had a lower concrete compressive strength. And in summary, we can say that ignoring the perforations in the midspan, well, the midspan is where the pre-stressing is fully developed, led to the overestimation of cracking capacity of the units. As you can see, like the section 1, that the perforations are ignored, we got an overestimation of the capacity. And also openings on the top and bottom legs of the units had the highest, like section 2 and section 4, had the highest effect in reducing the cracking capacity in correspondence to the direction of applied load. Again, all 4 cross-section geometries are evaluated for the flexural capacity of the SEAHIVE specimens, and in order to measure the flexural capacity of PC SEAHIVE units, we conducted a comprehensive PM analysis on each section, and we also had a linear strain distribution assumption in the cross-section. And still, the formulations for pre-stressed GFRP bars are not available in ACI 440. And in the meanwhile, the complex geometry of SEAHIVE does not allow the direct use of formulations from ACI 318. So as a consequence, the proposed formulations for section analysis of pre-stress GFRP reinforced SEAHIVE are presented here under pure compression, and at the points where neutral axis is between the lowest and highest fiber, like between the balance, above the balance point and below the balance condition, and also the formulation for determining the balance depth. And at the end, these are the PM curves that were obtained from the specimens with 72 megapascal and 43 megapascal concrete compressive strength. And as you can see, the ultimate compressive force highly depends on the geometry of the cross section, and it also depends on the concrete compressive strength. So at the end, the compressive strength is obtained, is calculated using the PM curves for each of the specimens. And we can say that although the ultimate compressive capacity of PCC hive units was significantly affected by perforations, the openings did not influence the ultimate flexural capacity. So the compressive capacity was highly influenced by the geometry, but the flexural capacity was not that much influenced, and the significant factor affecting ultimate flexural capacity of PCC hive units were the pre-stressing level of the GFRP bars and perforations on the top and bottom leg of the units. For instance, we can say that the specimen D had the lowest concrete compressive strength compared to specimen C, but since the pre-stressing level at specimen C was lower, so we get the lower ultimate flexural capacity for specimen C compared to specimen D. Here we also want to evaluate, I can say like the further evaluations of the SEAHIVEs will be conducted under the numerical work that my colleague Husam did. Now I want to further explain the field evaluation of the SEAHIVEs, and credits of this work partially goes for Professor House on Eco Reef project in Miami Beach. So there are some practical usages of SEAHIVE, and as a part of Eco Reef Artificial Reefs project, cluster of 24 SEAHIVE units were installed 800 feet offshore in Miami Beach in 2023. And the physical monitoring report in 2025, right here, revealed that scouring and settlement of structures revealed the scouring and settlement of structures from the gaps between them. And consequently, individual units towed inward towards each other. And it was also observed that the long-term stability of SEAHIVE units was improved by using chains. Like here, they were chained together. And placing of geotextile material under the units to avoid settlement and reduce scouring is also suggested. At this part, I would like to introduce another technique for improving the performance of SEAHIVE, and this is the wrapping SEAHIVEs using FRP strips. It leads to increased flexural capacity due to the added confinement, and it also helps clustering units together with glue, and it also leads to enhanced bond between longitudinal GFRP reinforcement and concrete. So now, since the clustering of the SEAHIVE units makes it easier for the installation, one of the techniques that is currently being tested and also studied is using the cluster of FRP wrapped SEAHIVE units. FRP wrapped units enables us to bond them easier together using Sika glue, so they are glued together from the parts that FRPs are wrapped. And also it makes their installment very easier, and any configuration of the SEAHIVEs under the in vertical and also horizontal configuration can be created by using two main configurations, A type and B type. And any cluster configuration can be made by combining these two main types. And there are also two different tests that are currently being conducted on the cluster of SEAHIVEs, which are longitudinal shear and also the transverse shear. And the main purpose of these tests is to measure the bond of the Sika glue between the FRP strips. And these tests are currently being done, and it's going to be the topic of our next research. So it was until here, and from the next slide, my colleague Husam will explain the numerical investigation. Thank you very much.
Thank you, Khashayar, for your presentation. Let me share my screen. So to start talking about how these SEAHIVEs, like the complex geometry, behave in the way we conducted it, because like this numerical investigation is only for internal pre-stressing, which is using pretension. Firstly, like there were two models were developed, one to represent D1, which has a compressive strength of 42 megapascal, and the other model was to represent the remaining 6 units, which has a 72 megapascal compressive strength. A constant pretension value of 300 megapascal per rebar were assumed for both models, which is similar to D1 and A1 and A2 after assuming 20% for pretension losses. And a linear elastic model was like chosen to represent the GFRP. This assumption comes because it depends on the type of the loading. So in our case, the loading comes only in the fiber direction. So a linear elastic model should be sufficient to represent the behavior. And concrete damage plasticity was chosen to represent the behavior of concrete, which is a very sophisticated model that accounts for tension and compressive behavior of concrete and cementitious material. And bonding between the concrete and GFRP was choosing using embedded reinforcement, which assume a full bond between them. Since like pretension were applied, we don't need to account for the slipping model account for GFRP, which is unnecessary and would create some numerical problems. And for embedded reinforcement, the way it's usually interact between GFRP and concrete, it maps the nodes of GFRP into concrete, which make it pretty easy to define inside the model. And regarding the element type, hexagonal mesh were achieved using partitioning because in Abacus, like Abacus was used for this model, it needs some partitioning to be able to create a uniform mesh. A linear interpolation function were used, which is optimum for numerical stability and remove any singularity to happen. Mesh size was chosen to be 25 millimeter, which is very efficient to have a model that remove any like artificial to happen during loading. And For GFRP, we choose truss element to represent it, which allow only for axial, no bending action, and 3D break for concrete, which is an 8-node element. So the boundary condition we're choosing, it's kind of tricky for deep beams because there's both flexural and shear action that happen in 4-point bending. So there are, firstly, like we need to have loading plates with friction to allow to have the right stress transfer inside the model, because not having it would create some artificial problem where you loading or supporting the structural system. And in the supporting, partial restraint in the longitudinal direction is needed to develop the shear action that happened in the ultimate failure. So in the support, we have like the transfers and out of plane are fully restricted, and along the longitudinal direction, partial restraint are applied. First, let's talk about the results. In the first step, only pre-tension were applied. The pre-tension were created using thermal loads, which allowed to the rebar to be tension and then transfer it using the embedded reinforcement into the concrete. As you can see, the rebars are being pre-tensioned from a distance from the end, which remove any singularity at the corners that could be created. And another aspect, if you look into the concrete itself, the SEAHIVE, you can see that the yellow zone and the green zone represent where pre-stressing is maximum. And along the perforations, there are no pre-stressing because there are no rebar in there. And if you look into the behavior, like after flexural cracks start to be inducing, which is in the second step, you can see a pretty good matching between experimental and numerical work, whereas there are 3 flexural cracks are being created, and same way in the right. And if you look into the bottom model, you can see which is have a higher tensile strength. As we said, there were 2 models, so you can see a more flexural action in there. If you look also into the stress distribution after having the flexural crack, you can see like an almost linear elastic response in the top, which is represent the normal stress along the longitudinal direction, which is the right way to look how stress is being transferred. If you look into the top, the blue represent where compression is created, and in the bottom where red is induced, it represents where tensile stresses are induced as well. So it shows a pretty good matching and it create a more insights how the response happened. If you look down, there is von Mises, which is actually that's a criteria for metals, but in Abacus, when you define a concrete damage plasticity, the von Mises would represent how concrete damage plasticity behave, which is the constitutive model I already defined. If you look into it, it shows a similar consistency between the normal stresses, because in the top you can see compression is developed as maximum where red zone is located. And if you look into the bottom where is the blue and light blue, this is represent where tension is happening. If you look also into the failure damage and the ultimate behavior, you can see how transition happened from flexural behavior into shear action. You can see also the shear action happens at the 2 ends, which something didn't happen in the experimental, but that's since we have a numerical model, it represents an idealized behavior. And if you look into the second model, you can see a more intensified flexural action because it has a higher tensile rupture, which allow for more flexure to happen. And also in here, you can see the stress distribution during the ultimate stage. As you can see, the von Mises, which is the concrete damage plasticity, shows the compression strut happening in the top of the specimen and extended into diagonally into the supports. And if you look into the normal stress, you can see a better representation how compression and tension is happening. You can see as well the compression is happening at the top of the specimen, whereas it's extended diagonally into the supports, and you can see all the other zones are red, which represents that tension happens and extended through the ends as well. which create the shear action that happens in the ultimate stage. If you look also into the plastic strain in both direction, which is firstly the plastic strain along the longitudinal direction, it shows how the flexural action happen, how there are many vertical cracks is going on. And if you look into the second direction, which is the along y direction, which is the transverse, you can see how shear is created, how the horizontal cracks are being developed. And in the end, you can tell that these two actions creates or generates what's happening in the end. If you look also as well into the deflection, you can see that the maximum deflection happened in the middle of the section, which give you 6.82 millimeter displacement. And you can see also as well at the two ends, there are some displacements happening to the top, which is typical of what happened during a 4-point bending testing. And if you see in the force deflection response, we have all the units in here and the two models I'm talking about, which is D1 in numerical, which is in black, and A1 and A2, the numerical in blue. And it shows the very good matching, I think, with the experiment. And it captures many aspects that's really happened during the experiment, and it makes it a right judgment to create some partial restraint along the longitudinal direction. So in the linear elastic behavior, you can see the model is sustaining flexural cracks when it reaches its first crack, and then you can see a drop that happen, which shows the transition from flexural to shear, and some displacement is created until the failure where shear govern in the end. There are many conclusions can be made from what happened during the numerical analysis. One of it that the compression strength doesn't matter that much, since if you look into here, D1 has a much less compressive strength, which is 42 to 43 megapascal, and A1 and A2 has 72 megapascal, but still that didn't change the ultimate load failure. Since premature shear failure is governing, then you assume, or not assume, like you know that the full capacity of compression, it wouldn't be created. So even if you look before into the compression in the ultimate stage, you can see in here it's reaching only 35 megapascal, while the maximum compressive capacity is around 72 megapascal, which give you the conclusion that shear actually develop and create the ultimate failure without utilizing the full compression or tensile behavior. And if we can also talk about one important aspect, that the numerical simulation exhibit a largely symmetrical behavior, but in the experimental, we can see unsymmetrical behavior where shear failure happen only at one end. This difference highlights what's going on during the experimental can be pretty different because of the micro configuration of the SEAHIVE specimen inside, where are some local weaknesses can happen, and different concrete consistency it does exist, which make the crack happens or the failure happens only at one end. And you can, that's something can be assumed unachievable during numerical analysis unless I create any artificial imposing. And lastly, we can say there's a huge satisfactory level of agreement with the experimental results, and it's induced that all the modeling techniques were sufficient to capture the loading behavior. And that's it. Thank you.